Welcome to the last session of this digital system design module. So, in this in this session, we'll cover these three important aspects. One is like we'll see how to do digital design for algorithms, and then we'll take an example of GCD computer, and then we'll try to implement that GCD computer in Verilog. So, before starting this session, let us summarize what we have done so far. So, uh, we understood how to design combinational logic. We also understood how to design state machines and small sequential logic. But the end goal, if you remember, in our first session when we took, we see that digital design is essentially the backbone of all the electronic system. So whatever electronic system we see, they're mostly based on our digital design. So be it IoT nodes or media processors um, or automotive cars, automation in the cars. So most of them, like they'll have a fair amount of digital systems. Now, when we are designing for such a complex systems, then we also require to build complex hardware and sometimes custom hardware. Okay, so let's first understand what is the meaning of custom hardware. So you see there are two kind of hardware. One we call programmable hardware, which is kind of a processor, and the other which is non-programmable, which is called application specific ICs. Now, so any application, when we try to make it programmable, so that means it can run on processors. Okay, so these processors are programmable, so that means any applications we can write. And these days, at least like after research of some 40-50 years in processing, now we have processors which are clocked at very high frequency. That means they're decent fast. So you have a processor up to 2 gigahertz or 3 gigahertz of frequency, and plus the internal micro architecture of the processor. That means a lot of techniques in the out of order execution, multiple issue processor, multiple function units, branch prediction, prefetching. So all of these techniques makes this processor extremely fast, extremely efficient. Further, to reduce the power, we also see a lot of multi-core processors. So these multi-core processors are power efficient as well as they can give us a good performance. On top of it, compilers are also quite efficient for high-level languages, so they exploit all kind of parallelism. Okay, so this way, the most of the applications, when we write any algorithm or any application, so for those applications, we see all these processor, and we also see a variety of them. So we have on one extreme, we have a Xeon processor from Intel, which is a server kind of processor, or other i3, i5, i7, which are also good for application processing. On the other extreme, we also have embedded processors which could serve like a small microcontroller in IoT chip, or they could serve as application processor in mobile devices. So because of this whole big spectrum, so whenever we need to run any application, we can select and choose a processor, and then run our application on that processor. Still, the idea here is to motivate that can do we require some sort of custom hardware to run these applications? Okay, the reason sometimes we would like to run these applications or algorithms on uh, very specific IC or very specific hardware designed just for that particular algorithm. Okay, the reason is we have. I'm writing here at least 3-4 reasons, but there are many more. Like processors may not be able to exploit all kind of parallelism. So sometime we'll see through the slides that there are some kind of parallelism which cannot be exploited by processors altogether. And also because processors will have a lot of external parts, additional part, like it will always fetch, then will decode, and then even if we would require 10, 15 instructions or 100 instructions, it will always execute, it will always design for some thousands of instructions. So because it has much more area, much more undesirable functionality for that particular application. So this undesired functionality would require additional hardware, so would require computation power as well as area. So this will become a costly option. Okay, so the other important thing is that although we have these processor, as I said, will have this out of order execution and all the high performance stuff, but as we go for high performance stuff, the processor become very power consuming. So for example, you see that all the Intel processor or i5, i7, i9 based processor, they consume more than 50 watts. Okay, they'll deliver performance, but at the cost of high power as well as high cost. When we require these applications to be ported in embedded system or in a small area constraint, small power constraint, then many of these processors, many of those functionality which is there in high performance processor will not be available in those tiny devices. So sometime because of that, we would require to design our own hardware for executing that application. So this idea itself is slightly challenging to understand. So we, for example, we see a lot of applications around us. Okay, the most popular, like we see this whenever we start C coding or algorithm coding, we are introduced to sorting. So can we imagine that hardware would be running these sorting algorithms completely without the help of any processor? So the hardware would be taking those arrays and then will do all that memory processing, jugglery, comparing, and then storing it in some other part of the memory. So everything, when it is done by hardware, then we can call that particular hardware as a custom hardware for that particular application. Because hardware is designed for one particular application, it is also called application specific integrated circuit. So now we are designing a hardware for one application, so that means it won't have any other undesirable functionality which is not part of that application. So it would be area efficient, and it would be performance. It would also be able to deliver high performance, because if we try to run the same sorting algorithm on a processor, then processors are always sequential, so they will run instruction by instruction. Although some sort of parallelism can be achieved by out of order execution or multiple issue processor, but otherwise instructions are executed one by one, so their performance is limited. But here the performance would be limited by what kind of operations can execute in parallel. Okay, so because of that, we expect these custom hardware to be much more high performance than the corresponding programmable solution. Okay, so now less area, high performance, less area also corresponds to, usually also means that the power would be less, but further power can be reduced by optimizing the circuit for power. Okay, so with all of these things, this particular custom hardware will become a very small IC which doesn't require the whole processing. Now, based on the application, there could be multiple kind of parallelisms that can also be exploited. And we can also design specific function units. So for example, I was taking example of the sorting. So in the sorting, we can design a special unit which can swap the locations, and if we can go further, it can also swap directly from the memory. It can read from memory location 1, memory location 2, and directly swap it there. So this way we can also identify that instead of going with the standard addition multiplication units, we can also go for a custom unit. We can identify that what kind of processing is repeated again and again in those applications, and those applications, then how we can bind together, how we can identify those units which can accelerate the things further for them. Okay, so why do we use this custom hardware? So mostly it would be used in some sort of embedded application where the scope of application is limited to one or two algorithms. For example, when we have IoT nodes, it just collect the data. So we can have that custom hardware which is just collecting the data and interfacing it to the outside world. So similarly, based on the applications, we can identify that do we require a full-fledged processor, or should we design a custom processor? The advantage of custom processor, as I will summarize here, that it would be very efficient in performance, would be definitely small in area, as well as it will consume less power. Now, why it should be giving higher performance? Because in the programmable solutions, we'll execute them one by one. Here we can exploit different kind of parallelism which could be present in the processings. So what are the different kind of parallelisms? So for example, given a system which we would like to implement, given an application we would like to implement, we can identify that which all modules can run in parallel. So these modules uh, can only be designed in hardware. So in software, they're equivalent to different tasks. So if in the hardware we can identify that let's say encoding as well as decoding, both of them can run in parallel, so then we can have two different modules. And any two modules in hardware, they will implicitly or basically inherently, they always run in parallel. Okay, now at the second level, you can also have these modules could be pipeline, means the data can keep on coming and it can keep on processing this data. And within the module, there could be the operations which can also run in parallel. So there is no sequentiality. Sequentiality would be imposed only because of dependency. So whenever in the algorithm something required to finish first, and then the result is generated, and that result will go to the output of the operation, then because of to support that dependency or to honor that dependency, there would be sequentiality introduced. Otherwise, whatever can be done in parallel, that can be done in parallel, and that these sort of parallelism would definitely increase the performance, and overall design could be efficient. So with all these degrees of freedom that designing an application with different modules and identifying parallelism, identifying pipelining, and also selecting how much parallelism we need to actually implement. So all this degree of freedom creates complexity also. Based on the design objectives, objectives could be area, it could be performance, it could be power, it could be actually cost. Cost is also a factor of, as we have studied in our first session, it depends on like a number of pins or total amount of area, and fabrication cost, NRE cost, how much volume we need to produce. So based on all those things, the cost would matter. So based on the cost, based on the objective function, then we can design. So I can understand that whatever description I'm saying, because it is oral and there is no graphics, we are not able to understand. So let's take one example. So yesterday somebody was talking about that how do we identify or match the pattern if it's a 2D input of data. So let's take that particular problem little forward, and let us say we would like to have some sort of a matching algorithm. Okay, so how do we match in a 2D? So 2D input. So let's say this 2D input is an image. So how do we represent image? Image is actually n cross m pixels, and each pixel is usually 8-bit value or 24-bit value. So each pixel may be RGB or YUV. So because there are 3 pixels involved, so we sometimes consider them as 3 different images, one image of Y, another for U, another for V, or one pixel would have 24-bit value. Okay, so let's consider that it is only grayscale and only one pixel is there of 8-bit. So this 8-bit pixel, and there would be height cross width, that many number of pixels are there. Now, these are very regular operations in image processing, that there would be a weight or there would be a 3 cross 3 filter, 5 cross 5 filter, or 9 cross 9 filter. So these filters can be used to identify the patterns and to do smoothing, to do edge detection, or essentially like identifying the patterns or doing some operations over the image. Now, what this filter or this particular operation will do is, so let's say there is a 3 cross 3 filter and there is some image. So what it will do is it will, every weight would correspondingly multiply to the 1 pixel of the image. So here, let's say W11 would multiply to A11, and W12 would multiply to A12, and W13 would multiply to A13. So similarly, this whole 3 cross 3 area of image would be multiplied with a weight or with our filter. Now, after doing multiplication, it would also be added and sometime divided by 9, or doing averaging, or sometime doing quantization. So multiplication plus addition, multiplication of these 9 values and addition of this the product of multiplication is one definitive operation which would be there in almost all the filters. Now, this multiplication of this multiplication is also called a convolution operation. So this convolution operation, 3 cross 3 into the 3 cross 3 part here, now it would generate one particular output. Okay, so we can also write this output at any particular position ij would be equal to a I plus k j I plus k j plus l into w k and l, and the summation would be over k and l. So this is a very generic equation. So instead of 3 cross 3 filter, even if it is 5 cross 5 or 7 cross 7 or 11 cross 11 filter, this particular equation will work. What this equation is telling, that when we multiply this filter onto this image and we keep on shifting the filter. So for example, initially we are multiplying with this area A11 to A33, and to calculate the next output we multiply this whole filter with A12 to A34. So this area we would multiply, and correspondingly we will have an output image which would be like there would be some 2 pixels less. So let's say the input image is, let's say, m cross n, the output would be m minus 2 cross n minus 2. So because we are multiplying with 3 cross 3 filter, so to remove that, sometimes we add zeros on the boundaries so that input image size and output image size is exactly same. Okay, so why I am telling all these things, that if I want to do this operation, onto a processor, and that's what we do. So if I want to do this operation in processor, so all these multiplications and then additions, plus there would be for loop for k, for loop for l, and similarly one for loop for I, one for loop for j. So this I, j, k, l, these for loops would be running in sequence, plus there would be some overhead which would be involved. Overhead of calculating this I, j, k, l, and updating these variables, plus accessing this weight from a memory, um, accessing these image values again from the memory, and there would be caches involved. Memory would have a larger latency. Now weights cannot be stored in a register, so because of all of these things, it is a time consuming, or it would lead to a slow process. And if we require such kind of image processing in a real-time application, real-time applications means we would like to do it very fast, less than a fraction of seconds, less than so in sort of milliseconds, so that we can see the effect quickly, and we can also process the output. So then this programmable solution will not be sufficient. And let us say in that case, we would like to design a hardware solution. This hardware solution will also be called accelerator, because it will make this image filtering or image processing much faster process. And you can also imagine that this kind of image processing things are used in plenty around us. So wherever, whatever we see using eyes, those things can also be seen using camera, and we would like our cameras to identify what is being seen. Okay, so using this image processing, we would like to identify objects, we would like to read the characters, and do the text processing, OCR kind of thing. So all those things are quite important and are there in the embedded domain. So we would like to do them as fast as possible. So that is why we may require image processing or image filter accelerator. Okay, so given we would like to implement this whole image filter as a complete hardware solution, there is no software involved. Okay, so let's try to spend a couple of minutes onto this particular problem. Then we see that can we design a hardware solution for this, and if we can design, from where we can get the performance. Okay, so the first thing we see is that that to generate one output pixel, we would require these 9 multiplications. Yeah, so W11 would be multiplied to A11, W12 for A12. So this is all for pixel number 00. Now there would be 9 multiplications, and similarly there would be 8 additions, actually not 9 additions, but 8 additions would be yeah. So these 9 multiplication and addition just for one processor, plus there would be 9 memory accesses for weight, 9 memory accesses for image for one pixel. Now this would keep on growing as we will multiply it with number of pixels. That would be the minimum computation which is required. So how can we make it fast? What we can do is we can do all of these multiplications in parallel. They're not dependent on each other. All of these pixels here are independent, and all these weight numbers are also independent. So there is nothing which stops me from multiplying all of these filters to all of these image values or pixel values at the same time. What is limiting me? There are two things. One, I would require a hardware resources. I would require 9 multipliers. That's the area cost. The other thing is I would also require 18 memory accesses before I can do these 9 multiplications at the same time. So 18 memory accesses at the same time, or in a single clock cycle, or for a single operation, that would require that my memory should have that much of bandwidth. My memory should be able to support that much wide accesses or that many number of ports. So the first requirement of having 9 multipliers is not very difficult, not complicated, but having 18 memory ports or that wide memory access would be a challenging thing. Okay, so let's talk about that particular memory access in a while. But let us assume that we have these 9 multipliers. Now, after these 9 multipliers, what would be the additional thing? We have to now add all the multiplication results. So I want to add 9 numbers, and how would I add it? Either I can do a sequential, I can have a accumulator will add number 1, then number 2, number 3, number 4. So that means it would require at least 8 cycles. Okay. So otherwise the alternative could be I can create a tree because in a tree it would take at least 4 different variations. So I would have first I can add 4 numbers, then I can add 2 numbers, 3 numbers, and then 2 numbers, so on and so forth. So it would take at least 4 different cycles or 4 different additions cycles. Plus the resources are also more. Now, because our focus here is to design a custom hardware, so can we design a custom adder or custom adder unit that can take 9 inputs? It may look little off that how can we have an addition which can take 9 different inputs? Okay, so if we see the literature, if we see around, then we see that anyways, whenever we do multiplication, we have so many of these partial results which we add. So for example, a 32-bit addition would add those 32 partial results. And to add those 32 partial results, some specific type of carries which are called specific type of adders which are called carry save adders, these have been designed. So these carry save adders are very specific adders which can take multiple inputs. So even here we require 6 inputs to be 9 inputs to be added. Those 9 inputs can be added together by just looking at what can be added in parallel. So these very these specific units can be created for specific applications. So here I can say that if I have availability of this 9 parallel multiplication unit, and assuming that somehow from memory I would be able to add. We'll talk about memory in a while. So in one cycle I would be able to add all the multiplications, and in one cycle I have this very custom adder unit which can take 9 inputs and can add all of them. So in one cycle I can add all of them. So essentially in 2 cycles I am able to do 1 pixel computation of output. Okay, so again, these 2 steps of multiplication and addition, these 2 further can be pipelined. So when I am adding the for 0th pixel, I am 0th output, I am adding, I am doing multiplication and then addition. Then for the first pixel, I can start doing addition, and then so when I'm processing addition for pixel number 1, addition for pixel number 0. So for pixel number 1, I can start doing multiplication. So this way, this pipelining will give me a throughput that every pixel can produce me output in every single cycle. Now, write bandwidth I require is I just need to write 1 pixels. The now challenge which I still need to address is how I can deal with this. How can I deal with the memory bandwidth issue? So this memory bandwidth issue can be addressed by doing 2 things. One, by storing the by storing all the weights in registers. So rather than storing the weights in the memory, I can have custom registers for all the 9 weights because they don't change. They are stationary, or for one application or for one particular type of image filter. So let's say it is a Sobel filter, or edge detection filter, or smoothing filter. So the weights for this particular filter is going to be constant. So I can load all of these weights in starting in these registers. Done. So I don't require these accesses. Now the access which would be challenging is how can I access 9 memory reads every time. Okay, so for that, what the solution which is proposed is called is line buffers. So line buffers are special kind of buffers. So basically, instead of keeping things in memory, uh, here we don't require caches, or we can create our own custom memory hierarchy. So as a part of that custom memory hierarchy, we can create these line buffers. So in these line buffers, what we can do is, for example, here we require 3 cross 3. So what we can do is we can initially store 3 full lines. Okay, and after that, every cycle, what we need to do is every cycle for we would require one additional. So let's say we have this this is there. So every cycle we would require just one pixel. Now rest of the things would be there. So every new cycle, if I get one additional pixel, then I have this data in my buffers. And if I need not to get it from the memory, but it is there internally in my buffer, so I can do this task of performing the memory read directly from these buffers. So the bandwidth reduction, bandwidth has been reduced to only reading one pixel from the memory at one time. How is it possible? So I'll repeat. So essentially what we are doing is initially we are storing 3 full even like we just require two full lines, and after those 2 full lines, then we also require 2 full lines and these 3 additional elements. And whenever we are computing the next element, we just need to bring one element from the memory, and then next element will be with the arrival of the next element, we would be able to compute this 3 cross 3 pixel. So then you can argue that what is the size of this line buffer? You need to keep on increasing this. So the size of this line buffer is also constant. So you can also remove the pixels which are not further required here. So whatever is required, what would be required, we are storing it. So it's a sort of a cache very specifically tailored for this particular application. So essentially, if we have this kind of a hardware, then one pixel, one output pixel, or one computation, one innermost computation can be done in a single cycle. Throughput would be single cycle if we are given this specific hardware as well as a specific multipliers and specific addition which can take. So this is the power of a custom hardware. Now let's not stop it here. Can we find further more parallelism, and can we find further more performance? Of course, yes. So right now, whatever we are talking, it is able to compute only one pixel at one time. Why not to compute multiple pixels at the same time? So let's call this computation, which is computing one pixel, is called pixel processor. So can we instantiate multiple such pixel processors? Can we say one pixel processor is calculating for this half the image, and rest of the pixel processor is doing for the another half the image? Of course, yes. So the only challenge would be we would require multiple more resources. If we give more resources, we can instantiate more pixel processors. We will be able to do linearly fast with them. And then can we do even better? So we can also, what we can, this I have already discussed. Wait, yes. So multiple pixel processors can be there, and then along with the multiple pixel processors, this pixel level processor is called data level parallelism. Now, what we can further do is, if there are multiple images, so these images can also be processed in parallel. So there could be some pixel processors which are being processing image one. There could be another set of pixel processors which are processing image number two. So this is called task level parallelism. So, or thread level parallelism. So this way, the first one was instruction level parallelism. So where we are able to find operations which can be done in parallel. So operation level parallelism, data level parallelism, thread level parallelism, and plus pipelining. So combining all of these four things can give us the performance as desired. Now, overall performance would depend on how much hardware, how much area we can spend. And we can see that it would be a kind of a linear curve, that if we keep on providing more area, if we keep on providing more resources, then performance will keep on linearly increasing. Okay, so and depending on our budget of the resources, budget of the area, we can say that, okay, this is what we want. We can limit our performance requirement, and then we can, within that budget, we can focus on the other issues of power and delays. So with this example, we can understand that yes, if we have some specific application, then how we can think of exploiting maximum parallelism, exploiting what kind of things can be done in parallel, um, and suitably designing our unit. Now, the next question which should come to us is there a process? Can we do it systematically? Do we need to do some kind of a courses or some kind of a methods we have to learn? The typical algorithm is like we have to first split all the applications into multiple modules and then define the interfaces and interconnections of each. Say that what would be the input and output of these modules, how one module would interact with the other modules, and how they would be accessing memories, which type of memories would be there, whether we would have one big memory, or for each array or for each image we would like to have a different memory. So that memory architecture, because it's a custom chip, so we can have a custom memory hierarchy also. And then once these outer interfaces are clear, then we can focus on each module. Then we can see that what are the resources required to execute that module. We can create a data path, control path, and then state diagram, and then implement that state diagram. And so essentially we can design module by module. So the first thing is to divide things into modules and then work on modules. Okay, so there is it looks easy to say that dividing into modules and then designing those modules, but it is quite challenging. So first of all, dividing into module itself is challenging because we don't know which things can run in parallel. And major challenge in designing those independent units, designing these independent units is our mind actually think in a sequential manner. So like we have been studying these algorithms and for 5, 6 years, 10 years or 20 years. So and all these algorithms, they are made in a sequential manner. They have not trained our mental faculty to think parallel. So this thinking ability is the biggest challenge, that we are not trained to design parallel algorithms or design parallel modules. So whenever parallel things happens, we don't know which would come at what time, which signal will come at which time, and we don't know what would be the dependencies. So identifying those parallel units is one issue, and then identifying the dependencies. So identifying dependencies and creating these modules is more or less a similar process. So because we would like to identify those modules as independent which has least dependency, and we have to bring out those modules out of an intricate algorithm which looks like a close knit tree. So the one which will have least dependencies would be forked out, and we would say that okay, we should design that particular thing as a single module. Now, what would be the dependency of that module onto other module? And when we design inside the module, then even better understanding of these applications is required. So, for example, we should know if there's a if-else condition, whether if will occur more regularly or else part will occur more regularly. Whatever occurs more regularly, we'll try to create fastest path for this, because we know that the else part will come, let's say else part is less frequent, so else part will come once in a while, so it can take multiple cycles, but the if part, which is more regular, can take the fastest path. So understanding those if else conditions and saying that which is more regular, if there is a loops, how many times usually this loop will come. So if we, even if we don't have a clear idea of the number, but a range of number would be helpful in understanding that what is the loop count, so we can design around it. Okay, so and the example which I gave in in last few slides, that this image processing filter is probably the easiest most, because it has essentially all kind of parallelism: data level parallelism, instruction level parallelism, and loop level parallelism, and uh, thread level parallelism. So all kind of parallelism were there, but not all the applications may have such kind of parallelism, and that too very explicit. So we have to find out where the parallelism is, why there is a dependency, why the application is slow. So breaking those dependencies and thinking out of box, we thinking for solutions how those can be done in parallel requires some kind of a creativity also. Okay, so the last most issue, which is also quite important, that once you design it, designing it is not only not sufficient, but we also need to verify, we need to fabricate it. Or so this whole process of design, verification, fabrication is huge. Creating a new design, verification, this itself is a big process, and then fabrication is a time bound process. It takes its own time. So the whole, all of these things can be offset, because they would in turn terms into cost. So if that particular module is required by so many people, if the volumes are large, so this kind of a cost can be offset, and that's why we still see people using these kind of units. So is there a solution? So for first 3-4 problems, that because understanding, deep understanding of applications, like each and every piece of code, each and every line of the code, understanding each and everything is somewhat difficult, and finding that parallelism and having that kind of a creativity. Can there be a more systematic way? Can there be a solution for that? So one solution which has been proposed is, we call it automation. We simply automate this whole process of design. Now, if we know that how to break things into modules and how to find parallelism, so if all of those things are there in the books, why not to translate those books into softwares? So these and that was the genesis, and from there these softwares came into picture. These are called high-level synthesis softwares. So they automatically take the high-level specification in form of C, C++, System C, BlueSpec. So these high-level specification language, they take them as an input, and then they process it. They identify what kind of instruction level parallelism are there, what kind of data level parallelism is there, what kind of thread level parallelism is there. Sometime, and all of these things are done with the help of compilers. So sometimes compilers are not that smart because compilers are conservative in nature. Whenever, for example, they will see a pointer, they will say there's a dependency. Whenever they see an array, unless those uh, iterators, indexes are not affine, we we cannot identify whether that particular there is a dependency or not. So to override that, sometimes user inputs can be given, and user can say that okay, these two things are parallel. Go ahead with this kind of optimization, and even user can support. So basically, here user and the compiler, they are complementing each other. They are helping each other to make design faster. So these designs are usually correct by construction. Because they are correct by construction, the verification cost is very less. Okay, so this automation, and plus for verification, they also generate the test benches and all those additional scripts and supports automatically. So that also reduces the design time. So this way, this high-level synthesis is one option that has been a ray of light for custom hardware. That if we would like to synthesize custom hardware. So, for example, these days, this CNNs, convolution neural network, or deep learning platforms, they are quite popular. Now, if we need to write all of those things in a very log, in a RTL manner, and synthesize, it may take years. But then you can we have seen in the research that people have written them very efficiently in C, C++, and then synthesized it, and they were able to come up with a very efficient hardware which is as good as people have done using custom or handwritten Verilog. So this high level synthesis tool, the meaning here is the high level synthesis tools are sufficient, and also uh, are optimized, so they can beat easily a human or custom written, manually written Verilog for many cases. So there are a couple of these solutions which we see around, and these are the most commonly used one. Xilinx have that Vivado HLS, which is a part of, I think, their free software also. Catapult C is a offering from Mentor Graphics, and Forte Design. So this is the offering from Cadence. So these if sometime we would like to use and we would like to create our own custom hardware accelerators, we can give these also a shot to design our own. Okay, so now the concluding remarks here is see we see this custom hardware usually used for mainly two purposes I observe. So one is it is used for creating different interfaces. So it is mostly control oriented work. The other and some sort of a glue logic between two different interfaces. The other the major application of this custom hardware is these accelerators. And these accelerators, to offset the cost, these accelerators are not created for one application, but they are created for domain of applications. So when we say, let's say I want to create a hardware accelerator for edge detection in images, that may not have that value. But if we say that we are designing a hardware accelerator for image processing, so it supports n number of different image processing applications. So uh, domain of applications and creating a hardware accelerator for those domain of applications is much more interesting and a good usable solution. So again, in this deep learning domain, you see that's why there is a lot of neural processing units or neural accelerators. So these accelerators, they are able to accelerate not only one particular deep learning application, but whole set of deep learning applications. So whatever deep learning algorithms are there, they can be ported onto those accelerators. So so these deep learning accelerators is one example, but yeah, in history, this video codecs were also quite a popular example. So they were heavily used. So these MP4, MP3, these formats, whenever people used to see on their embedded devices, image rate used to be very very less, or this refresh rate used to be very very less. So they had to use these accelerators so that they can have a real time feel of video processing, these game consoles and video processors. So that's why these video codecs were quite popular. But with GPUs becoming commoditized, or like being easily available, so these video codecs are less used as a hardware accelerator. They're used only in the very specific scenarios where low power is required because GPUs consume so much of power. So in low power cases, embedded devices, we still use hardware codecs. The other area where I see use of hardware accelerators is um, in encryption or security domain. In security domain, for example, you have a hard disk which is fully encrypted. Now, if software is decrypting and then sending you the information, you will see that your hard disk is so slow, but you still require a hard disk which is fully encrypted to make it secure that nobody steals your data. So that's why if you have a hardware accelerator there, you won't feel your hardware your hard disk is completely encrypted. So user is able to see the data um, in a usable way. So there is not much of the performance issues, and still we are able to keep our things secure. So these are the couple of domains where we keep on seeing this hardware, like hardware design, custom hardware design, which would be required. Um, and seeing the last 15-20 years, these applications keep on coming. So today it is, let's say, machine learning, deep learning. So tomorrow there would be some other applications where we would require this custom hardware. So it's a good skill to learn how to design applications, um, or how to design hardware for algorithms, or how to design algorithms for hardware for a specific application. So with this, I would like to close here for a moment and to take your question.